right, here we're actually recording a video on the camera and a video on the screen capture. Try to sync it simultaneously. And to start with, I'm going to turn the pulse width modulation back to a high. That'll get the motor rotating. And I'm going to go into standby. Notice it's turning clockwise. If I change these two signals in opposite positions, now it's going in the opposite direction. Let's change that again. Makes a little bit of a different sound because of the wear of the brushes. So into standby. Now notice when I take it out of or put it back into standby, the motor will coast to a stop. It maybe takes half of a turn before it actually stops. Whereas in the brake or fast or short stop, you'll see it stops much quicker. Let's try it in coast. Okay, actually in coast it takes about a half a turn to stop, and in fast stop it takes less than a quarter of a turn to stop. Okay, it stops quite quickly, and the motor begins to act like a generator. Okay, so that's it for the video on the phone, and let's continue with the screen capture. We're going to go into the block diagram, and I'm going to open up the DAC Assist. Oh, we'll have to stop the program to see the DAC Assist, but this is the program. It's basically just controlling 4 bits of information into the DAC Assist, and this shows you that line 4 is controlling pulse width modulation, 5 and 6 are the direction, standby is on 7. And I think that's all for part number 1. This is part B of the demo, where we're going to use motor brake or fast stop. Okay, this is the part B program. I'm also recording the camera. Recording the motor with a camera. And so to start this program, I have to make sure that standby is pressed in. The motor will start to turn. Okay, and this program, as it says, when it stops at 3600, the motor will come to a stop. And you'll notice that it stopped about 60 degrees after we signal it to come to a stop. Let's just start it again. So I'm going to restart the program just to see if we get that same number, at least approximately. So I'm recording this as well. So when it got to 3600, 66 degrees after that, the motor physically came to a stop and stopped generating pulses. Okay, let's go to the block diagram. I'm going to stop the video. And in the block diagram, there's a flat sequence structure, and there are 3 parts to it. In this first part, I want the motor to be stopped, so I make standby a false. I wait a half a second. Then it comes into this middle while loop, and there are 2 DAC assistants. One is reading the quadrature and coding. Let's open this up just to see it, but we'll have to stop the program. And if I open this up, one of the things you'll see, and I know you won't be able to see the whole screen, but it's connected to, if I can bring this up, no, I won't be able to bring it up, but it's connected to programmable function interface 0. That's basically digital IO 0 and digital IO 2. It's set for decoding of times 4. So it's testing on the positive and negative edges of both channel A and channel B. And it tells me here that I'm going to have 90 pulses per revolution. And that makes sense for that motor because I'm using the motor that generates 3 pulses per DC motor revolution, and it has a gear ratio of 30:1. So the 3 times the 30 gives me 90. And it's going to be in units of degrees. So every 90 pulses or every 1 revolution, I should get 360 degrees coming out of my program. So I'm going to close this off, go back to the program. And so this orange wire right here is where I'm going to be measuring the encoder frequency. Okay, or sorry, not the frequency, I'm measuring the degrees. So coming out of here will be degrees. So if I run the program, I'm going to add a probe. Okay, I'm going to add a probe on this wire, and we're running, and it's telling me that the probe right now is at 0 because the motor is not turning. So let's go back into the front panel and get the motor turning, but it's going to be very short. So back into here, and it tells me that the number I have is 3.659 to the exponent 3. So that's really 3,659. If I go back to the block diagram, you'll see that number right here. But back into the block diagram, sorry, I went to the front panel. Let's add another probe right here. And this is telling me that it's true because this number is greater than the 3600, so that goes true. This gets inverted over here and goes false, and that's connected to the pulse width modulation. So that's going to give me the fast stop, okay, which it did. And that's enough for this part. All right, in this video, we're going to show you the operation of coasting to a stop. And it's pretty much the same program as before, but instead we're controlling the stop with the standby instead of the pulse width modulation. So let's give this a try. So turn standby on, and I'm waiting for the program to reach 3600. When it does, the motor is signaled to stop using the standby. And it's actually stopped in the software, not through this push button. And you'll notice that it turned about, well, 360, maybe 148 degrees. Let's just do it one more time. Maybe get a bit of an average. Run it. Starts at 0. Okay, and at 3600, it will stop. And if I take the number 3808 and subtract it from 3600, it's around 200 degrees greater. So it's taking a lot longer to stop than it did with the quick stop program. So let's have a look at the block diagram. So I'm looking at the block diagram, and I'm actually going to show you that the signal is coming from the encoder, and we're going to put a probe at a couple of different places. I'm going to put a probe here, and I'm going to put a probe right on that wire. Okay, so I have a couple of probes. One of them is measuring the signal coming out of the encoder, and the other is measuring the signal coming out of this greater than signal. So I actually have to start the program in the front panel, and I'm going to run the program, press standby. It's at 0 right now. Go to the block diagram, and you can see the number increasing here. When it hits 3600, causes this signal to go false, or actually this signal to go true. It gets inverted here, and it stops the motor from turning, because these two signals would have to be true for standby to be turned on, but this signal goes false, standby gets turned off, and coasts to a stop. And you'll see that there are 3 parts to this program. It has a flat sequence structure, and we're starting the motor here off because standby is false, and then we do the stuff in the middle, and then at the end of the program we disable it by making pulse width modulation off and standby off, in the directions just opposite each other. Okay, so this is the end of the part 2 program, part B program, where we're doing a coast to a stop. Hello, this is part 4 of the demonstration, where we're going to use the pulse width modulation capability of the MyDAC to control the speed of the motor. So I'm actually going to have a video of the motor as well, which I've just started the video. And what we're going to try and do here is we have to first of all make sure that these direction pins are different. Okay, and that's causing the motor in this case to turn in a clockwise direction. Okay, so it's turning clockwise, and I can control the speed, the duty cycle, either in two methods. This method, okay, I'm speeding it up and slowing it down, and you're seeing the feedback. This is what it's actually sending out as the pulse width modulation. And I can only go to 99% with this program. Okay, or I can do it with these push buttons. This gives me 40, 50, 60, 70, 80, 90, and 99% pulse width modulation. Okay, now, and if I wanted to change directions, I would do that here, and I can change the pulse width modulation frequency, but I want you to keep it at 100 hertz, which is a period of 10 milliseconds. Now, let's have a look at the block diagram, but I'm going to stop the motor. And the best way to stop this program is to press the stop button. Okay, and then I'm going to go to the block diagram. And there's a lot of stuff in this program, and I definitely don't expect you to know everything here. But what's happening, let's try to explain what's happening, is that this first block here, you have to make sure that your MyDAC is being selected. So it should say MyDAC 1 counter 0, and you can change it by doing this if you have to. And then what these are separate, what are called DAC assist functions. So this is creating a virtual channel. This is setting up timing. This is telling it to start. And then we have something called an event structure. An event structure is very useful because it allows me to basically have almost like a software interrupt. When something happens in the software, it'll cause it to go into this event structure. And the way I've set it up is that I have many different events. Okay, changing a value on this push button, or this one, or this one, or this one, or moving a slider will cause these things to change my program. For example, if I go to 50% value change, which means if this button changes, it's going to place a value of 0.5 into the counter duty cycle. So it's going to change it to 0.5. And it kind of happens on the fly, just as the program is running. I can also do it by a change in value from the duty cycle slider. Okay, and that's going to be the value from the duty cycle slider. So if it's 40, 50, 60%, that's what'll change. But I have a change in each of these things. So for example, at 90, it's going to go to 90% duty cycle. And if I go to 99, so realize that this is actually 99%. It's 0.99 times 100, which gives me 99%. And then the other parts here are pretty much like the other program, where I'm controlling analog in 2 and 1 with 5 and 6. Standby is being controlled by 7. But what you do have to change here is you have to make sure that the pulse width modulated signal on digital I/O 3 of the MyDAC is connected to the pulse width modulation signal on the motor controller, the TB6612. Okay, and as I said, understanding kind of what I've circled here is not critical. I will not ask you questions in any tests. A little bit more complicated, but very useful to get things to operate kind of dynamically as I'm running the program. Okay, so that's the end of part 4 with the program C, changing the pulse width modulation. Okay, in this example here, I'm running the Part C program where I'm controlling the pulse width modulated signal to the motor controller. So it's very important that you are connecting the digital I/O 3 pin, okay, that outputs pulse width modulation on the MyDAC. It has to go to the pulse width modulation A pin on the TB6612 controller. Now this program can do a duty cycle anywhere from, I think, 0.1 or 10% all the way up to 99%. What I've done here too is that you can control the duty cycle with a slider or preset values of 50, 60, 70, 80, 90, and basically 100% or 99. Okay, so what we want to do when we're doing this test is also measure the DC voltage across the motor to see what happens when you modify the pulse width modulation. So let's make some measurements here. So I'm going to start off at 40% duty cycle. And you can see that my duty cycle signal is on the bottom channel. And you'll notice that things don't seem to be triggered on the bottom channel. And that's because the two signals are not synchronized. The pulse width modulation on the bottom is being created by the MyDAC, whereas the top signal, channel A, is a measurement of the encoder signal. And that's the one we want to trigger on, because I know when I'm sending out 40%, it has a period of 10 milliseconds, and 40% of that time it's high. If I wanted to stop it just for a second, okay, and you could measure the period of the signal, but you can see from here to here, that's about 10 milliseconds. So that makes sense. 4 of those 10 milliseconds, it's high. So let's run it again, and we'll put it back into auto. Okay, and then so right now, this is feedback coming from the pulse width modulation functions telling me that it's at 40% duty cycle. So let's boost it up to 50. The motor should turn faster. Okay, and I know it's turning faster because the cycle time is less. Now let's go to 60. It's even less now. 10, 70, 8.6 milliseconds, 80, 7.2, 90, 6.2, and the fastest speed we can get. And this is with a voltage of about 9.5 volts. Okay, and now we're at about almost 100% duty cycle. And I can even change the voltage, and you'll see the speed go up. So this is with 9.5 volts, and that's with 10 volts. Okay, we're getting 5.2 milliseconds with about 10 volts. And you should be able to figure out that time. So let's do it for one case. And let's go to 90%. So that's 90% pulse width modulation. All right, in this example, the period of the encoder signal, the top signal here, is 5.9 milliseconds. And there are 3 pulses for every revolution of the motor. So if you take that 5.9 milliseconds and multiply it by 3, you'll get about 17.7 milliseconds. If you do the inverse of that number, 17.7 milliseconds, you're going to get 56.5 rotations per second. Okay, so we just did the reciprocal or the inverse to get the number of rotations per second before we had the amount of time or the amount of seconds for one rotation. Okay, so the DC motor is turning at 56.5 rotations per second at this time. And if I want to know what that is in RPMs, I'd multiply it by 60. So 56.5 times 60 gives me a DC motor RPM of around 3390 rotations per minute. And then if I divide that number by 30 because of the gear ratio, I'm getting 113 rotations per minute of the output shaft of the motor, 113 RPMs. And if I divide that by 60, that's about 1.9 rotations per second. So almost 2 rotations per second. And I'm looking at the motor, and that seems to be right. And if I want to know how long it takes for one rotation, I would get the reciprocal of that. So 1.88, 1 divided by 1.88 gives me about 0.53 seconds. Okay, now if I wanted to confirm that, it's kind of a higher speed to do this, but let's give it a try. I would use a stopwatch app on my phone and measure the amount of time it takes to do 10 rotations. So in this case, it would probably take me about 5.3 seconds to do 10 rotations. Divide that by 10, and it's going to give you 0.53 seconds. And from that, I can calculate all of the various settings. But I can also do it with, so I'm going to put a tachometer on the end of the shaft, and the tachometer is going to measure the speed in RPMs. Let's see if we can get a good reading, and it's visible on the camera. Just going to hold the motor, press. Just takes a second to read. And it's reading about 110, 111. I just want to make sure it reflects there properly. And so that's the reading from the tachometer to check the speed. Hello, this is part 6 of the demonstration where we're going to look at a little bit more details to do with the Picoscope. So I have the Picoscope running and it's in auto mode and it's triggered on channel A, which is the top blue trace. And you can tell because this is in blue. And that trace is set to plus and minus 10 volts, which means from the bottom, minus 10 volts, to the top, plus 10 volts, there's a difference of 20 volts. So 20 volts divided by 10 divisions gives me 2 volts per division. So this is almost at 0, and this is going up to 3.3. So this is coming out of the my DAC because it's the pulse width modulated signal. It's not sitting at a very good 0 volts. I could have some issues with grounding, but still fine. Everything's working correctly. The pre-trigger point is right in the center, but you can see if I move this to the left, I'm getting now a pre-trigger point that's 10%. This really depends on what you're trying to measure. You're measuring the time high, the time low, and so on. So I'll just keep it in the center for now. And you can see the timing starts off in the center. Anything before that point is a negative value. Anything after that point is a positive value. So I can see right here that this represents 5 milliseconds per division. This is 10 milliseconds per division, and my trigger threshold level is 2 volts. That's where that yellow diamond is. You have to be really careful with this software. When you start it, that trigger point might not be where you want it to be. The other thing to check is a lot of students have difficulty with this, but I'll ask that the ground be on a certain line. So I'm going to shift this up and down. Notice I'm on the blue side. And I want to get it in the center, and I want it so it lines up at 0 volts. Now, I don't want the two signals to overlap, so I'm going to move this up and down, but I just want it so that I get 0 on this line over here, and my signal is down at the bottom. Okay. Now, the time per division, as I said, is 5 milliseconds. So across the screen would be 5 milliseconds times 10 division, that's 50 milliseconds. 25 after the trigger, 25 before the trigger. Okay, and now if I select none, you'll notice that both traces move left and right because it's not being triggered. Or I could select single and it triggers once, and sometimes that's a good way to be able to see the signal. Or I can get it to repeat. Okay, and it's kind of like auto when there's a continuous signal. Or like I said, I could have none, but it's not triggered. So I like to leave it on auto. And let's say I wanted to measure the pulse width modulated signal. I would trigger on channel B, but I want to make sure that trigger level is halfway in between the minimum and maximum. Okay, so it's triggering on a rising edge. I could get it to trigger on a falling edge by doing this. Okay, and if you look at the timing, it triggered at 0 milliseconds and it went all the way up to 10 milliseconds. So that's telling me my period is 10 milliseconds, the frequency is 100 hertz. That's my duty cycle. Or sorry, that's my period of that signal. So the duty cycle is 90%. If I wanted to measure it with cursors, I could do this sort of thing. Line it up on a cursor, move the next one over to that next falling edge, and you should see that it's 10 milliseconds. Okay, almost right on. If I want to measure voltage, I would bring these cursors down just to see what voltage I'm getting here. The other cursor is here. Okay, and up here it's telling you the difference in time, the difference in voltage, and so on. So a lot of very useful information. The other thing just to check is that I'm going to click on this box here. You want to make sure your probes are set up for standard and times 10. I've done that for both probes. And oops, no, I don't want to turn the generator on. Probes standard times 10. What that does is when you have it set for times 10, you're going to have less loading added when you add the scope probe to your circuit. Okay. All right, in this example, I've used my slider set to about 55% duty cycle. And that's causing my motor to turn at a certain speed. And visually looking at it, it seems to be about 1 rotation per second. So, and the other thing I did to test that is I counted how many rotations I get in 10 seconds and divided by 10. And I worked it out to be about 1 rotation per second. So my voltage is set to 10 volts DC. And I'm drawing about 166 milliamps at this speed. Sometimes at a slower speed, you will get more current. So let's figure out the time here. So it's taking about 11.1 milliseconds for one of the periods from the encoder. So times 3 would be about 33 milliseconds for 1 revolution or 1 rotation of the DC motor. To find out the reciprocal of that, or how many rotations per second, I would take 1 divided by 33 milliseconds, and that gives me 30.3 rotations per second. And if I wanted it in rotations per minute, I'd multiply it by 60. That gives me 1800 RPMs. And then if I take that number, divide it by 30, because of the gear ratio, I would get 60 rotations per second. Okay, and that makes sense. That, or sorry, 60 rotations per minute, which is 1 rotation per second. Okay, so that's the end of the Picoscope measurements with program C. All right, this is part 7 of the Lab6 video demo, and we're running program D. Okay, Lab6 part D, and you can get these programs from Brightspace. So right now the motor is not turning. I don't know if you can hear that or not, but it's not turning, and I'm getting an encoder frequency of 0 rotations per second, 0 rotations per minute, and the encoder period is reading infinite. So nothing's turning. And what I expect to see when I run the motor is that this thing will show me the output shaft RPMs. The DC motor, I'm measuring DC voltage for the supply to the motor is 10 volts right now. You can see that here. And this is going to be the differential voltage across the motor. So it's very important to understand this part, that the differential voltage is measured with channel 0 minus and channel 0 plus across the motor, just across the motor. And that's called a differential measurement because there is no reference to ground. Whereas the motor supply voltage will have a reference to ground. You'll connect channel 1 minus to the ground circuit, the ground of the circuit, sorry, and you'll connect the channel 1 plus to the supply coming from your power supply to the voltage on the board. And then once that's all connected, we can test it out. So all the time I'm getting the supply voltage. Now I'm going to run the motor in a certain direction, and I'm getting about 122 RPM. Okay, and you should be able to figure that and do the math so that the encoder period is 5.5 seconds. And remember, we could change that to milliseconds if we used SI notation. I might change it when we stop the video. And that's giving me rotations per second of 60. And DC motor is rotating at around 3,600 RPMs. Okay, so all of those measurements are making sense. And since we're going in a counterclockwise direction, I'm getting about plus 9 volts. And I'm actually going counterclockwise. So now if I go in the other direction, I'm going to stop first. And notice my voltage changed, and this went to a green, indicating clockwise direction. All right. Oh, I forgot to make one change, which I'll do and come back. Okay, I made that change here to SI notation, 2 digits of precision. And I want to make sure that based on the way I've wired the motor, and this may change for you as well, I want it so that it reads, this thing only goes green when I'm going clockwise. And if I go, so I'm going to change it to clockwise, and now this goes green. This says clockwise, and my motor voltage is about around 10 volts negative. But when I go in the other direction, I should get 10 volts positive. So I'm not going to check off this lab until all these meters read correctly. You know how to calculate the time based on the period to get encoder frequency, rotations per second, DC motor RPMs, and the output shaft RPMs. And making sure that when this is set to clockwise, direction says clockwise, counterclockwise, direction says counterclockwise, and only when you move it to clockwise does this green light come on. And if I'm looking at the prototyping board, the red LED comes on as well, indicating that everything is okay. The other thing I want you to notice when you're doing this part of the lab is the differential measurements here. Okay, so this meter is measuring the difference in voltage, and we're sitting at about -9. When we go in the other direction, we were at about plus 9.5 or 10. The DC supply doesn't change. It stays at that voltage all the time. It's just the motor voltage that's going to change. It's going to reverse when we go from clockwise to counterclockwise. So now let's look at the block diagram. All right, this is a very complicated block diagram. Well, parts of it are. The only part I don't really need you to fully understand is this part here, where I'm just opening up a virtual channel for a DAC assistant. And what this allows me to do is, instead of using the DAC assistant to modify things, I get a little bit more flexibility with these DAC MX controls. So these are functions for the counter timer. So I have to specify which channel and which device I'm using. So there's actually a little pull down window here that I can open up. Okay, and these are the different counters, but my DAC only has one counter 0. So now when I run this program, well, I'm going to have to go back to the front and click on run, and then back into the block diagram. What I want to do is point out a few different things in the block diagram. So this wire right here is where you're getting your encoder frequency. So I'm going to put a probe on that line, and you can see over here that I'm getting 185 hertz, okay, which is making sense from what I saw on the front panel. Let's just switch back to the front panel, about 185 hertz. Going back to the block diagram, I want to point out a few different values here. So that was one of them. I happens to be on number 7. Unfortunately, the LabVIEW software doesn't reset things. So let's kind of follow the stream. So the frequency is coming out of this wire. And over here, this wire is still at 185. So if it's turning, 185 is going to be greater than 1. And if it's greater than 1, that goes true. We can even look at that probe. It's true right now. And it will select the running text to appear at the status. So that just tells me that it's running. Okay, if I continue along here, coming out of here is my encoder frequency. So that's still 185 hertz. It's getting divided by 3. So that's going to give me 60 hertz or 60 rotations per second. And that's what you'll see on the screen. Okay, 60 rotations per second. Okay, these are very approximate. So going back to the block diagram, after it passes through here, I'm going to multiply by 60 so I get the DC motor RPMs. Go back to the window. You'll see the DC motor RPMs is 61. Okay, so that's fine. Back to the block diagram, and I could put a probe here, and that's probe number 9, and you can see that this would be my rotations per minute of the output shaft. Now the other signal to look at, which is important, is this one coming in here. This is coming in from the 74HC74, and it's being used to let me know the direction. So right now direction is false, coming out of the direction pin, and then it's going into this select, and since it's false, it's going to give me counterclockwise and make the text appear as saying the words counterclockwise. And down here, my direction is still false, so that's going to turn off the direction light. So let's just look at that over here. And the direction light is turned off. It's telling me counterclockwise. So let's just make a shift. Run that again. Now if I go to the block diagram, then things are going to change here. So coming out of here, which is probe 10, that's a true. And that's going into the select, so it's going to take clockwise and send it out to direction. Now the motor differential voltages we can measure here as well. -9 on that. The motor supply is +9 because of that direction it's turning it. So the probes can be very useful to analyze all these different signals. Okay, and you should be able to explain everything I've explained here, and adding probes, that's something I want you to be able to do in the lab. So back to the front panel. I'm going to, this time, since I'm not using pulse width modulation, I'm going to slow down the speed. Okay, and then go back to 10. I don't want to exceed 10, that's very important. In part A and B of the program, basically we're going to have this connection where we're using digital I/O0 and digital I/O2 to measure pulse width modulation. And we're connecting 4, 5, 6, and 7 to the direction pins, sorry, 5 and 6 to the direction pins. Digital I/O7 is an output on the MyDAC going to standby. So a high will get the motor running, a low will place it into standby. Digital I/O4 is going to be used to control pulse width modulation, but we're not actually feeding it pulse width modulated signals. We're just making it go high or making it go low. Low to fast stop, high to run. And the motor supply, it's coming from probably a power supply, probably from the ones used in CA219B. Set it to around 10 volts is fine, but don't go over 10, and maybe set this a little bit higher than it says on the screen here, maybe 200 milliamps. But that's called VM or V motor. You also need 5 volts connected to the MyDAC supply. And these will be output pins on the motor controller, motor A. I think your chip might say something a little bit differently, but these will go to the red and black wires on the motor. Okay. There are two other wires on the motor. I think they're the brown and the green. You have to make sure you connect those to ground and +5. They are going to supply power to the Hall effect sensors. And there are two Hall effect sensors, channel A and channel B. They must have a pull-up resistor because they're open collector outputs. If you don't put a pull-up resistor there, it'll appear to be reading a logic low all the time because it's either at 0 volts or floating. Okay, so you don't want to leave it in that floating condition. There must be a pull-up resistor. All of the motors have a 30:1 gear ratio, but the motors with the white cap produce 7 pulses per revolution or rotation, and the ones with the black cap produce 3 pulses per rotation. So that's the kind of circuit you'll have for parts A and B. This is an example of using the motor with the Hall sensor that has 7 north-south poles. So let's say that the encoder was measuring a period of 3 milliseconds. That would mean that one revolution would take 21 milliseconds, or 3 milliseconds times 7, which if you determine the reciprocal of that 21 milliseconds, that would equal to 47.6 rotations per second. And then if you multiply that number times 60 to convert it to revolutions per minute, that would give you 2857. And then the gear ratio is going to slow down but increase the torque of the motor. And it's a 30:1 gear ratio. So I would take the 2857, divide it by 30. That would give me 95.2 revolutions per minute. Divide that by 60 would give me 1.59 revolutions per second. And then the reciprocal, or the inverse of that, is 0.63 seconds per revolution. So that means in 10 seconds, it would rotate about 6 times. Here's an example of the 4 different scenarios. So we have part A, which is basically just testing out the motor. So you have to have a motor supply and the motor connected to the 2 terminals. And we're basically just sending out signals to standby, pulse modulation, and the 2 direction pins. On the next slide, this is part B. We're controlling the same signals as in part A. The only thing we've changed is added the encoder signals from the motor. Okay, the 2 encoder signals. Make sure that there is a pull-up resistor, or else this will not work correctly. Part C, pretty much the same thing for the encoder signals, but this time we're going to measure things on the, well, it says MyDAC scope, but we're going to change it to the Picoscope this semester. And we're measuring channel A and channel B so that we can look at the pulse modulation signal and the encoder signal. And what's important here is that digital IO3 does go to the pulse modulated pin on the motor controller. And this last part, part D, where the digital IO, the encoder signal is going to digital IO1 to measure frequency. Digital IO4 is coming out of 1Q, and I think that's pin 5. And these 3 signals are pretty much the same way they were before, but the pulse width modulated signal must be tied to +5 volts, so it's always enabled. And then this device, the 74HC04, has to have the 2 encoder signals, channel A and channel B, and the LED that lights up. And it'll be, if this signal is a logic high, this will be a low. So if digital IO4 is a high, which is then going to the MyDAC, if this is a high, the LED will turn on because it'll be a low on this pin. It'll be the opposite. Hopefully all this helps. Thank you.